Welcome back everyone to Machine Learning CMPT 726. So last time we actually covered a lot of things. We started off finishing up the probability review by talking about Gaussian distributions and how we can look at the marginal and conditional distributions, basically how we can compute them very easily given the joint distribution. And that was done by using the block notation. Then we moved on to probabilistic models, which is a different kind of model compared to what we have seen before, at least before last class, in least squares regression. So we looked at the concepts of likelihood and the log likelihood, which allowed us to compute the gradient of the likelihood more easily. Actually, to optimize the likelihood more easily, we saw that when we try to take the gradient of the likelihood, that was a very ugly expression, but after we logged the likelihood, the math became much simpler. Then we moved on to maximum likelihood estimation. So using the log trick, we were able to do this, and then we saw that basically it looks exactly the same as minimizing the loss function from ordinary least squares. Then we talked about treating parameters as not as a single fixed value, but as kind of a probability distribution over different values. And that was useful because it allowed us to kind of incorporate prior knowledge about the parameters. For example, smaller parameters should be more likely and larger parameters are going to be increasingly less likely. So given the prior, we used the Bayes rule to obtain the posterior distribution over the parameters. And based on that, so by maximizing the posterior estimation, we were doing maximum a posteriori estimation. So the result of doing this is actually the same as minimizing the loss function in ridge regression. So that's basically ordinary least squares plus L2 regularization. In general, we also kind of briefly discussed the connection between square loss and the Gaussian observation noise. So the maximum a posteriori estimation was actually giving us a single estimate of the parameter W. So that was called the point estimate. We also contrasted that with full Bayesian inference, which instead of providing a single value of W, or another letter we commonly use is theta for the parameters, in full Bayesian inference, we actually try to obtain the full posterior distribution. In general, that's actually quite difficult to do. But in some very simple cases, we can actually do this, and you will see one very, very naive example in assignment 2. So now let's kind of, before we move on, let's review a little bit. So take 2 minutes. I think this should be a bit faster. So which of the following statements about the difference between MLE and MAP parameter estimates is true? So take 2 minutes to do this. Okay, let's go over these. So first, MLE does not depend on the prior. That is true, whereas MAP does. That's true. So A is true. MLE depends on the likelihood function, whereas MAP does not. So actually the first part is true, but the second part is not true, because MAP actually depends on the likelihood function as well as the prior. So basically, let me go back a little bit. So this is MAP, right? We want to maximize P of theta given D. So we have both the prior and the likelihood here. So actually B is false. Okay, next, the derivation of MLE does not use Bayes' rule, whereas the derivation of MAP does. That's true. So just to recall, the MAP used Bayes' rule in order to kind of flip the conditional distribution. So this is basically using the Bayes' rule. We were just looking at this, right? So we wanted to write the P of theta given D in terms of P of D given theta. So that uses the Bayes' rule. Ridge regression can be interpreted as MAP, but not as MLE. That is true. So the regularization term in ridge regression corresponds to the prior distribution over the parameters in MAP. MLE does not have such a kind of a prior distribution. It's actually a uniform distribution, but that doesn't lead to any regularization term. Okay, lastly, MAP corresponds to optimizing a loss function with a regularizer on the parameters. Yes, that's true. Whereas MLE corresponds to optimizing a loss function without a regularizer. Yes, that is true as well. So we just talked about this. Okay, so the last one, E, is true. So hopefully you got all of these. So that was the probabilistic interpretation of linear regression. So now we're going to continue taking a probabilistic approach and look at bias variance trade-off. And this is related to overfitting. So remember, overfitting occurs when the model is fitting to noise in the training data. So if you look at these green training data, this is from the collab notebook we covered a few classes ago. All of these green points, they have some variation, but a lot of that variation is due to noise. And overfitting is basically having a model following all the noise around. We saw that when overfitting occurs, different training data sets that are actually generated, in our case, from the same data generation distribution will result in very, very different models. That means very different optimal parameters, right? So basically we generated two sets of data using our data generation process, the same data generation process, which is noisy. When we fit the same model, we actually get very different parameters. This is the degree 20 polynomial model. And this is really bad because a lot of times you'll see that because there's so much variation between the different parameters, we can easily get very large errors of prediction. For example, in places like this, or maybe over here. So what would be ideal is if we use models that typically produce accurate predictions on unseen test data, regardless of the particular training data set. Whenever we obtain a training data set, we assume, I guess one assumption we can make is that the training data set is generated by the universe according to some distribution. And that distribution is always the same, but there's going to be some noise, right? So when we collect some data set, we will happen to get one of these data sets, and we would like our model to make accurate predictions no matter what the universe happens to give us, as long as the distribution of the data generation process stays the same. That part is actually may not be true sometimes, but in this class we will assume this. Okay, so let's understand this mathematically. through the bias variance decomposition. So what we're going to do here is we're going to express the expected error, which is the thing that we want to be small, as a sum of the bias squared, the variance, and the irreducible error. So I'm going to go over all of these terms in a lot of detail, so going over every letter and what they mean. What we're not doing here is actually we're not deriving this. So I'm just giving this to you. I'm just saying this is the decomposition without deriving it. If you would like to derive it, please try it on your own. And if you have any questions, you can feel free to ask me either on the forum or in office hours. Okay, so we're going to take this as given and then look very closely at everything here. Okay, so the expected error depends on the unseen testing sample, right? So sometimes different samples could give you a different test error. So definitely depends on the testing example. It also depends on the model. Obviously, if we have a different model, then the prediction error will be kind of different, right? And the model, of course, depends on the loss function. So overall, the expected error also depends on what loss function we choose. For example, we can choose just the square error, or we can choose square error plus L2 regularizer, for example. Okay, so this is the thing that we want to make small. So let's expand this out a little bit to really get a mathematical definition of what we mean by expected error. Okay, so let's start from the inside. So D is the training data set, and L is the loss function as we covered. So the theta star represents the optimal parameters on the training data. So given the loss function, right? So basically, if you give me a data set and then based on my loss function, I can always compute theta star. Okay, so my model depends on the theta star. So having the theta star will allow me to take as input some test example and then output a prediction. So this whole thing, f of x and theta star of dl, so that is the prediction of trained model on a new testing example. And then we take that and then we subtract the possibly noisy label corresponding to the testing example. So this is kind of what would happen if we give the universe the ground truth model in some sense, x, and y would be the output of the universe. But then again, remember, this is kind of noisy as well. So then taking the entire thing inside together, this is a mean squared error on the testing example. There are a few things that are actually random here. For example, the dataset we collected is actually random. There's some noise to it. So every time we collect the dataset, it might be something a bit different. We just happen to have one sample dataset from the world or the universe. Also, y is also a random variable because every time the universe or the world generates y is a bit different. So that's why we take the expectation over these variables, so over y and d. So this entire expectation is the testing error averaged over training datasets compared to the noisy version of the label. So in practice, it may be very hard to actually compute this because we need to be given the same x, and then we need to train, and then we need to get many different data sets generated from the world, and then we need to train a lot of optimal parameters based on all of these different data sets. And then based on our trained model, the many different trained models, we have to compute how well our prediction is compared to the many different variations of y, kind of the output generated from the world or the universe. And then we would take the average of all of those. So that would be what this expected value means. Obviously, that's not really possible to do, but this is kind of a theoretical analysis, right? So we know we may be unlucky with a data set. We know that we could be unlucky or maybe lucky with the correct output. So then so theoretically, we can take the expectation. So we want to say, in expectation, how well our model is doing. So this is the thing that we really want to make sure is very small. Okay, so now we're going to decompose this into 3 parts: bias squared, variance, and irreducible error. So let's take a look at those. Okay, so starting here. So this is the prediction of the trained model on testing example, averaged over training data sets. Actually, that's exactly what it is. So F gives us a prediction, but the prediction is actually random. Even if our model is deterministic, the prediction can still be random just because that depends on the training data set, and the training data set is random. So then we take the expectation over all the possible training data sets, and that will give us the expected prediction of our model. We take that and subtract the noisy version of the label, so the average of the noisy versions of the label for the testing example. So we set that y could be changing. Every time you plug in the same x, y might be different. So then here we're taking the expectation over y. So we take the expected, we take the average prediction minus average label and then square that. So this is this term is called the bias squared. Again, this is more of a theoretical analysis. In practice, we just don't know whether we got unlucky with the data set. A lot of times you just have one data set, right? So this assumes that, so this expression is basically saying, okay, average over all the possible data sets. And this is averaging over all the possible labels, which is also not possible to do. Yeah, but in theory, we can look at this. Okay, let's continue. So next we have variance. So what the variance means is the variance of the prediction on the testing example over different training data sets. So remember, D, the data set, is random. Given some D, we're going to make some prediction for the input X. Given a different D, our prediction will be different because a different D will lead to a different set of optimal parameters, which will lead to a different outcome of our prediction. So this is a variance of all of those different outcomes that are affected by the different data sets. Okay, so this term is called the variance. So the variance is actually the variance in our model. And lastly, we have irreducible error. So this is just the variance of the different noisy versions of the label of the testing example. So variance of y given x. So this is something that we can't really do much about. This is just a result of the data generating process being noisy. Okay, so again, I'm just telling you this is a decomposition. We're not deriving all of this. We're just interpreting all of this. So we want the expected error to be small. So let's take a look at what happened with our overfitting example. So in the overfitting example, we know that overfitting is not good. It's not desirable. So the expected error is actually going to turn out to be large. So let's take a look at the decomposition for this overfitting example. So the bias squared is going to be small because if you average over all of these different data sets, you average over all the different predictions and then subtract the average the average y value from any particular input x, that's actually going to be very small, because this part is just the original polynomial without the noise, right? If we average out the variation, then all we get is just the original non-noisy polynomial. And now, if you train many different models based on many different data sets, you can imagine that this red curve will actually probably average out to something pretty reasonable. And the difference between the average red curve trained over many different data sets and the average green data points, that's actually going to be pretty small in this case. So the bias squared is very small. However, the variance will be very large. So remember what the variance means. It means the possible outputs of f given the same input x for different data sets. So as you can see, for different data sets, our f for some data points could vary a lot, right? So over here, for the same input, you could have vastly different outputs, and over here as well. So the variance is large. Okay, and then irreducible error, can't really do much about that. This is simply the noise that we had when we generated these green data points. Okay, so in the overfitting case, we have small bias squared, large variance. So adding everything together, we actually end up having a large expected error, which is not what we want. Okay, let's look at the other extreme case, underfitting. So in underfitting, obviously we also don't want this, but let's interpret it through the lens of bias variance trade-off. So looking at bias squared, again, bias squared is basically looking at the difference between the average prediction of the model given many different data sets. So what does that look like? So given different data sets, so if you average all of these models out, you will just get some average line that is going across these green points. And then we take that average line and subtract the average data points. So that's basically the not noisy polynomial. We can see that the line has a pretty big difference compared to the polynomial. So that's why the bias squared is very large. On the other hand, the variance of the model, so basically how much do the lines change when trained on different data sets? Actually, not much. So the line will wiggle up and down a little bit, but not too much. Unlike the previous example where depending on the data set, the red curve changes a lot, right? So in the underfitting case, the variance is small. And of course, in the end, we have the irreducible error, which we can't really do much about. So now adding all of these together, because the bias squared is large, overall the expected error will be large. So this is not what we want. Okay, and finally, when we do fitting just right, the expected error turns out to be small. And then when you decompose it into bias, variance, and irreducible error, all of these are going to be hopefully small. So in this case, the bias squared is small because if you look at the average, so the average of all the red lines, the red curves, they're going to match really well with the average of the data points. That's the unnoisy polynomial. So the bias squared is small. So now when we train on different data sets, we get a very similar red curve, right? We get very similar red curves. So the variance is small. And of course, we always have irreducible error. So in this case, we have small bias squared, small variance. So that gives us the best possible expected error. The major contribution to the expected error is just going to be the irreducible error. And that kind of makes sense, right? You can't, I mean, if we're fitting this red curve, if we're fitting a red curve to the data points, the best we can do is to have the perfect fit to the unnoisy version of the polynomial. But even if we do that, we are still going to get, our error will still be coming from all the noise in the data. So that's this part. So in the best case, we could have 0 for the first two parts, but then we will still have the noise as the error. So that kind of makes sense. Of course, in general, these are not going to be 0. There's still going to be a small difference between our model and the ground truth. That's just because when we train with different data points, right, there's always the noise will kind of shift. The noise will cause a small amount of bias. And of course, the variation in the different data sets will also cause the model to be slightly different every time. So these are small, which is good. But in general, they can't really be 0. So hopefully the bias variance trade-off makes sense. Ideally, we don't really want to trade off. We just want both of them to be small. Okay, but the trade-off just means that we need to add them together to obtain the expected error. Again, we're not deriving things. I'm not trying to tell you why this expression can be decomposed into this sum. I'm just saying that it can be decomposed this way, and we're simply interpreting this result. Okay, so takeaways. So expected error on testing example, mathematically defined to be this, equals to bias squared plus variance plus irreducible error. The bias is the difference between average prediction and average label of the testing example. The variance is the variance of the prediction on the testing example over the different training data sets. Of course, in general, we just have one training data set, but this is kind of a theoretical analysis. So suppose the training data sets suppose we have many of these different training data sets, then we don't want our model to have large variance. We want the model to be pretty consistent despite the different training data sets. In order to have a good fit, we want the expected error on testing example to be low. So that means both bias and variance must be low. Under this mathematical decomposition, overfitting is now well defined. So when overfitting, the bias is low, but the variance is high. Okay, bias is very low. The average red curve will match very well with the ground truth polynomial, but then the variance is high because different data sets produce very different red curves. When underfitting, the bias is high and variance is low. The average red line will not match very well with the ground truth model, but then the variation on the red lines isn't very much. And so I guess the takeaway here is that obviously I think underfitting we can detect that pretty easily, but if you want to achieve if you think that you can have a good expected error, you can't just have low bias. You can't just have a very expressive model, right? You also need low variance as well. So don't try to fit a very complicated model like a 20th degree polynomial, or maybe even a neural network, which is a very complex model, to some data that is generated by a very simple underlying mechanism. Okay, so that's the bias variance trade-off. Okay, now we're going to move on to nonlinear regression and optimization. So let's look at nonlinear least squares. So remember that previously we had this linear model, but we could also, but the mapping between x and y could also be nonlinear by using some features of x. But in the end, the reason we could still use least squares So the reason that we can still train W very easily was that y hat still depends linearly on W. So now if we want an even more complicated model, then you might ask, can we make the prediction depend non-linearly on the parameters? So for example, something like y hat equals W transpose X, all of that squared. So in this case, you will have many squared terms of W as well. So I mean, let's look at this from the probabilistic perspective as well. So let's say that we assume our data generating process is y equals f of x w plus sigma epsilon, where epsilon is the standard normal distribution. So now, following the previous slides on kind of probabilistic models, we know that the distribution of y given x, w, and sigma is going to be a Gaussian distribution with a mean of f of x w and the variance of sigma squared. So basically, we're going to assume this nonlinear model. So f could be a nonlinear function. And then we're going to start from this and go through the same steps that we did before to try to compute the optimal w. So the first step is going to be writing down the likelihood function. So this is actually going to look very similar to before. So the likelihood function L of W sigma D, that's equal to the product from y equal 1 to n of these Gaussian distributions. So 1 over root 2 pi sigma squared exponential of negative yi minus f of xi w all squared over 2 sigma squared. So previously our f was simply w transpose xi, but now we have a kind of a general nonlinear function here. So that's the main difference. So again, this we don't really like this product. So instead of looking at the likelihood, we're going to look at the log likelihood. And when we maximize the log likelihood, we can work out all the math that we did last time. Or actually last time. And then in the end, we'll get something like this. So the argmax over W of the log likelihood is going to be the same as argmin over W of the squared loss, right? And that's because our noise was Gaussian. So basically, this is a squared loss. The only difference is that before we had yi minus W transpose xi, and now we actually have yi minus f of xi w, where f could be a nonlinear function. For example, this one, or some other function. And now we would like to find w hat MLE, maximum using maximum likelihood. Okay, so going over this very fast because we have already seen everything. All the algebra is exactly the same, except that everywhere we had W transpose xi, we just have f of xi w. Okay, so then we want to solve. So basically, we want to minimize this function. So this sum of I equal to 1 to n of yi minus f of xw, this whole thing, we can just think of that as just some loss function where the variable, the only unknown is w, right? So we can write this more simply. In general, if we just use theta to represent parameters instead of w, again, theta is a very common letter for representing parameters. What we need to find is basically theta star equals to argmin over theta of some loss function L of theta. In the previous case, we just had theta equals w, and then our loss function L of theta was the same as the negative log likelihood. Okay, remember the negative was actually how we turned the argmax into an argmin. So L is known as the objective function, and L of theta is known as the objective value. So when we write down the problem like this actually becomes a much more general problem than a machine learning problem. This is actually called an optimization problem. So optimization is used much more broadly than in machine learning. Although in machine learning, we're basically always doing optimization. So optimization is used basically everywhere. Like in my field, in robotic path planning, that's an optimization problem. Machine learning is an optimization problem. Some of you may have taken linear programming. So when in linear programming, you were solving a specific type of optimization problem called the linear program. Other cases, for example, where some applications, warehouse optimization, where to put every product to maximize the utility of the same space. Is used in economics. How do we maximize the gain, minimizing the risk, right? So optimization is a very, very broad area, much broader than machine learning. In machine learning, we work with optimization problems that look like this usually, and this is actually called an unconstrained minimization problem. Minimization, because we're minimizing something, and unconstrained means that we just want to find the best theta with no restrictions on what theta is allowed to be. So in many other areas, we would actually look at constrained minimization problems. So for example, in robotics, we may want to minimize the fuel consumption, but then subject to the constraint that our robot cannot collide with obstacles, for example. Right? In some other applications like warehouses, we're constrained by the dimensions of each shelf as well as by the total space that we have, right? And then in some other areas, like another area that I worked on in research before was actually building optimization. So building as in buildings in the school or in office buildings. We would like to use the minimum amount of energy while keeping the comfort levels satisfied, right? So we're kind of optimizing the comfort levels subject to the constraint that the temperatures, for example, cannot be too high or too low. We're also subject to physical constraints. For example, the sun shining on one side of the building, heating it up, and then we're subject to the physics, constraints from physics, right? So basically, optimization is a very broad field with many applications, and machine learning is actually just one of the applications. And in machine learning, we're usually solving a specific kind of optimization, the unconstrained minimization problem. Okay, let's take a look at how we can obtain theta star or W star in at least in nonlinear least squares. So let's just write this out. Take some time to write this out. Okay, so in general we would like to find theta star, which is okay. Just making sure you can see. Okay, arg min over theta of some objective function L of theta. In our case, with nonlinear least squares, the problem, our specific instance of the problem is W equals arg min over W of our loss function, and our loss function is a square loss. We sum over all the data points, and then for each data point, we compute the difference between the label and what our nonlinear model predicts. Okay, so this F, nonlinear. Okay, So let's take the same steps that we did before with ordinary least squares. So the way we did that, how do you minimize something? Well, you take the gradient and set it to 0. So let's do that. So this is kind of repeating a lot of what we do, but hopefully also a little bit of review on some of the common mathematical manipulations we do. Okay, so first step, we take the gradient of the summation, and that becomes the summation of the gradient. Because the gradient is a linear operator, we can switch the, we can kind of put the gradient into the sum. So now we can continue taking the gradient. To do this, we use the chain rule. Okay, so the sum is still going to be here. So now taking the gradient with respect to this yi minus f of xi w all squared, the 2 comes down. So taking the outermost gradient, and then the inside stays the same. And then we have to take the gradient of the inside. The inside, the only thing that depends on w is f of xi w. So then we need to take, and there's a negative sign. So let's put a negative sign over here. And then we have the gradient of the function f of xi wi. Okay. And then we want to set this entire thing to 0. So previously, just to recap a little bit, previously f of xi w was just equal to w transpose xi. Okay, let me put all the arrows on the xi's. So previously with the f that is linear in w, we could actually evaluate this gradient here. And then as you have seen, we simplified, we took some steps to simplify, and then we eventually obtained w to be the pseudo-inverse, to involve the pseudo-inverse of the data matrix. But here, because f could be arbitrary, it could be, I mean, it's just in general nonlinear, we can't really solve this in closed form in general. So basically up to this step, we're good, but we cannot move further from this step. Okay, so that's basically the math. So taking the gradient of the square loss, gradient goes inside a sum, and then we do the gradient using the chain rule. 2 comes down, inside stays the same, and then the gradient of the inside with a negative sign out in front. Okay, set that to 0, but in general, it's really hard to write down w equals something. Okay, so then how can we, so that was just nonlinear least squares, but this problem is actually even more general. So in general, how can we find theta star equals argmin over theta of some objective function L of theta? So we tried to solve for the critical point analytically by doing math by hand, but we could not do that. Fortunately, we can still find theta using a numerical algorithm. And these algorithms are called iterative optimization algorithms. And the simplest version of these algorithms is called gradient descent. So the way gradient descent works is you just randomly pick some theta, theta 0. Theta 0, I mean, unless you're just extremely lucky, for sure is not going to be the right answer here. It's probably going to be really bad. But you're going to iteratively update this data. So from theta 0 to theta 1, and then theta 2 in general, from theta t minus 1 to theta t, until you get a very, very good theta t. So until convergence usually. So how do you do this update? In gradient descent, the way you do it is you take the previous theta, and then you subtract gamma t, which is a constant. We'll talk about that in a bit. So some constant times the gradient of the objective function evaluated at the previous theta. So this gamma t is a hyperparameter that we can pick, and is known as the step size or the learning rate. Traditionally, it was called the step size in optimization, but I guess because we're doing machine learning, maybe we should put in the word learning somewhere. So learning rate is a common term to refer to gamma t. Okay, so let's take a look at why this would work. So the way it works, again, let's say that our L function looks like this bowl-shaped convex function. So how can we find the minimum point? Well, we're just gonna plonk down some theta 0, and let's say that it happens to be here. From this point, we would like to find theta 1, the next theta. And the way we're gonna do this is to first compute the gradient of L. In this case, the gradient of L is going to be the green direction. Remember, the gradient of a function is the direction of the steepest ascent. So the green arrow is the direction where the function will increase the fastest. So given this data, we're actually going to go in the opposite direction of the gradient, which is the blue arrow. That's what the minus sign means. So the blue arrow is the direction of the steepest descent. We're going to move our point theta in that direction by a certain amount, gamma t. So then hopefully next time we have a slightly better theta 1. From theta 1 we compute a gradient again and then go down the gradient to give us theta 2, and hopefully eventually we can reach the bottom. Right, so for example, another example, let's say theta 1 was here, theta 0 was here. Every step of the algorithm, we're going to go down the gradient by some amount, by a step size gamma t or learning rate. And then eventually, once we get to the bottom, once we get to a critical point, remember that a critical point has the property that the gradient is 0. So when we get to the critical point, it will just be theta t minus 1 minus gamma times 0. So that means that the theta won't change. So when the algorithm has converged, we just return the value of theta. And hopefully that's going to give us a really good objective. Okay, so hopefully that made sense. This is the math. In your assignment 2, you'll be implementing some versions of iterative optimization algorithms. So then you're going to look at some code in your assignment. And then this is the picture. Okay, so now we have introduced another hyperparameter. Let's take a look at the effect of that hyperparameter. On the left, we have a step size that is too large. So here, when we plonk down theta 0, we have identified that we should go this way, roughly speaking to the right. But how much should we move in one step? Well, if you move too much, you would have overshot where the minimum is. So then you go to the other side of the bowl, and now the gradient is roughly speaking to the left. So now, if your step size is too large, then you overshoot again, and then you go back and forth. In this case, it may take you many iterations to actually get to the bottom. In the worst case, you may even go back and forth, oscillate, and then the oscillations might even become larger and larger, and you may never even get to the minimum. So the step size should not be too large. So compared to the step size that is just right, which is the same thing that we saw on the previous slide, we just go down directly to the bottom in a few iterations. On the right side, we have a step size that is too small. We are moving in the right direction, but it's just we're not making very fast progress. and maybe it will take many iterations, or maybe even an infinite number of iterations before we can get to the bottom. So obviously that's also not good. Okay, so let's talk a little bit about convergence. So there are actually two different notions of convergence. So there's the convergence to a target objective value. That means that as we run more and more iterations, the objective value gets closer to some target objective value, hopefully the minimum objective that we want. A lot of times we wouldn't necessarily know what the target objective value is actually. Okay, there's also convergence to a target parameter vector. So as the iteration number increases, so as we iterate more and more, the parameter vector gets closer to the target parameter vector, hopefully a global minimum. Okay, but typically we also don't know the target parameter vector. So this is really what we want, but we usually cannot do this. We cannot check for such convergence. So typically we need to somehow, without knowing the target objective value and without knowing the target parameter vector, we still need to detect convergence because we need to determine when to stop the optimization algorithm, right? So when to stop here. Usually we simply check this by looking at the change in the parameter. So we either compare the difference between theta t minus 1 and theta, and when that difference gets very small, we kind of say that the algorithm has converged. So that's one option. And another option would be to plug theta into our objective function L, and then see the change in L. Right? So the other thing we can do is we can keep on plugging theta t minus 1 into L, plug in theta t into L, and then if the difference between iterations is not very much, we could also decide that's the criteria for convergence. Okay. So it turns out that gradient descent, we can actually show that under certain assumptions about our objective function, we can prove that gradient descent will converge, and it actually has some convergence rate. Okay, but I guess probably we'll talk about this next time. So this is all for today. I'll see you guys next week. Have a good weekend.